Okay, so in this one, I'll have you try this one as well. We have an 80-gram acorn that's falling from a tree, lands on the ground 10 meters below with a speed of 11 meters per second. What is the average work done by air resistance during this fall? It would be faster if there was no air resistance, but this is the value that we get, for the speed when it hits the ground, but it should be faster. So see if you can solve for that. You're again going to set up your non-conservative work and see if you can find the average non-conservative work. Essentially, you're solving for the non-conservative work of air resistance here. So go ahead and pause the clip, and when you're ready, you can continue. Okay, so you set up your 10 meters there. There's nothing going on with springs here, so that's 0. We have the potential energy change, the kinetic energy change. Our final height is 0, right, at the ground. Our initial velocity and initial speed, it's falling from the tree, so the initial speed is 0, so that's 0. And so, we have our potential energy change and then the kinetic energy change. So there's 3 joules of non-conservative work here that take away from the energy. And then now we can find the average force of air resistance during the fall. So if you want to go ahead and pause the clip and see if you can calculate the force of air resistance coming from that non-conservative work. Okay, so non-conservative work is force of whatever kind of friction that you have, or air resistance, time displacement, time cosine of 180, negative 3 joules, and we get a frictional force of 0.3 newtons. And so during this, this fall, that's the average frictional force. It actually does change depending on the speed, but this is the average as it goes. Okay, so let's say we have a situation here. We have a jet that is landing at 57 meters per second. Its landing distance is 1,829 meters. And we want to find out what is the non-conservative force and the force of friction in this case. So we can draw, the situation here. The initial velocity is 57. The displacement's 1829. We have the, again, non-conservative work. So why don't you go ahead and solve this one and solve for what the non-conservative work is for this aircraft, and then see if you can solve for the force of friction. This is very similar to the last problem with the acorn. It's just a different orientation here with the setup. So pause the clip, and when you're ready, you can continue. Okay, so there's nothing going on with gravitational potential energy. There's nothing going on with springs here. It's pure change in kinetic energy due to non-conservative work. And when we solve for the non-conservative work, we get a lot of non-conservative work, 39 million and change joules of non-conservative work. And then if we solve for the force, we've got the displacement, we've got a cosine again of 180, friction's always acting backwards, and here's our frictional force. So so this one's similar to the last problem, but in this case we're just dealing with pure kinetic energy change. So if we consider this bike rider going down this incline, let's say we've got the mass of the bike rider, we have the height of the incline here, we have the length of the incline, which is 82 meters. We've got, let's say, a frictional force of 127.65 newtons, as well as an air resistance force. And we want to find out what the speed is starting, the speed at the bottom. So we have the force of friction, the force of air resistance on the bike rider, and the bike height is 48.2 meters. And so, go ahead and, calculate the speed at the bottom. You're going to have to add both frictional forces together for your non-conservative work, and then you can solve it from there. So go ahead and pause the clip, and you can try that. Okay, so the initial speed starting from rest, the final speed is 0 at the bottom. We have the non-conservative work here, and the total frictional force is 262.65. which we can place in here. So we have the total frictional force, we have how long it is, and the cosine of 180 because the friction is acting opposite of the motion. The final height is 0. The initial height we've got here is 48.2. And we're looking for the final speed. And we should get 23.88 as the final speed. Okay, so let's say now we're at the bottom, and we want to find out how far it's going to take for him to coast to a stop. So, you know, we have now at the bottom, we've got the mass of the bike rider, we have the coefficient of friction, and then we also have air resistance. The initial speed is 23.88. So what you're going to need to do now, you've got the normal force, force of gravity, right? You're going to have to find out what the frictional force is due to the coefficient. And then once you do that, you're going to add that to the force of air resistance. And that's going to be the total amount of force you'll use for the non-conservative work. And then you can go from there. So go ahead and pause the clip and see if you can figure out how far it will take for this bike rider to coast to a stop. Okay, so you should have set up your forces, you know, positive for, or actually we have two negative forces, right? Negative force of friction plus the negative force of air resistance. To get a force of friction, we need to take the coefficient times the normal force, which we get from over here. Force of gravity, normal force are balanced. 1127 newtons is the force, normal force. Place that in here, and we get a frictional force of 157.78 newtons, which we add to the force of air resistance. So the total amount of non-conservative force here is 292.78 newtons, which we can now take for non-conservative work. There's nothing going on with gravitational energy anymore, neither with the spring. And so we're looking for, you know, D, how far, and we have our frictional force, cosine of 180 is -1 here. We have our initial speed, and we have our mass. And so it's going to take 111.99 meters for this bike rider to come to a stop.